and we. All right. This is going. All right. So anyway, we went over this very briefly at the end last time, but like I just mentioned, we're going to quickly recap it, right? So expectation maximization, it's kind of, there's two steps to it, but they can really be semi-fused together. They're not always super clear which one is which. But they're always, you have to calculate an expectation first, and then you use that to maximize. But since that's the whole process, it's often more efficient to break them up. So if you remember, when we're looking for lambda, because of the way that it comes in, basically our update is going to look like the old one times a ratio, right? So we're not adding a delta, we're multiplying by a ratio. This is depending on your type of probabilities, and this is entirely because this is a Poisson process. It's going to look in this type of a format, right? And that ratio ends up being, a ratio. So there's kind of sensitivity ratio, but the individual sensitivities on the top are being multiplied by another ratio, which is kind of think of it, what actually happened over what you thought was going to happen, right? For each one of those boxes. And depending on how that adjusts, the correctness of it, it'll weight what the sensitivities were. And the ratio of those sensitivities will then do the update. And if you were overestimating it, then your expectation will be larger than the actual, so it'll cause the whole thing to shrink. If you were underestimating something, the actuals, of course, will be bigger than your estimations, and it will cause it to grow. And if it's a little bit of mixture of each, it'll appropriately weight it. So this kind of gives you the format. This is the last equation there, shows it to you in the format we're going to kind of be writing it as, right? So we've got the probabilities, the lambda, and our y, which is what we actually measured. Okay. Yippee-ki-yay. And I noticed this is just from the book, set the derivative equal to 0 for 936. And again, note, this is kind of where that expectation part is coming in, right? Because I've got my expected and the actual, that ratio. That does what you were thinking of doing, and the rest maximizes it. So, okay. So that's the last equation. I just copied it over and then broke it up into 3 parts. This really is the main part of what the expectation is, right? Because this is my current guess values times those sensitivities, however you want to think about them, right? That sets this denominator right there, right? And then I use that denominator to calculate the upper part of this, and then the sensitivity. So we have to calculate this one before we can use it here. So I'm going to need one set of sums here, and then another set to calculate these. So that's basically the ratio. Once that's done, then I just, this over this gives me my ratio for answer. So, all right. So let's start writing code. So this is kind of my setup for things. I noted again, the ones in yellow up there, that's going to be yours to kind of write some type of description on. Again, I'm trying to get you used to writing some documentation now. So the first little paragraph up there really is kind of describing the algorithm, right? So it tells you expectation maximization, and I give you a little bit of commentary of how it relates to the book. It's good to usually mention if you're using a particular methodology or other things. It's nice to give a quick mention of what that's going to do. Then I went through what those values are. What does each one of the parameters mean? Delta, I didn't do the last two. That's your fun to add. All right. And then you can see the two ends on the other side, one for the function and one for this while not done. All right, so you have a full loop, and the loop doesn't finish till the top of the next column, just because it doesn't fit otherwise. And in general, I do like this kind of not done format. Some people will string out the conditions to check on there, but I find that gets pretty unreadable. If you do the not done thing, you can do each individual term and then you can kind of combine them together, and it's much more documenting. If you've ever had to go back and read something where somebody strung a whole bunch of really hard to read conditions together, you know, they might as well just throw their code out after they use it, because it's, you know, it's basically worthless. So I'll give you a sec to copy what I got there. Yeah. Or you can kind of put my own commentary into, and I'll be posting these as soon as we're done. So you can always just cut and paste the commentary too if you want. But I think we got time. I'll give you a sec to type.
Is lambda 0 going to be a matrix with one value for each?
It'll be a vector.
Okay. Oh, but it'll be the size.
Yeah.
Okay.
But it'll be the vectorized version of the matrix.
Okay. So it's kind of like that IC flow.
Yeah.
Okay. That's true.
Because in this case, what you're getting, remember lambda is kind of a mean value in some sense. So it's what you think is in each box,
right?
The concentrations. So, you know, by using lambda, we're correlating it to a probabilistic framework that comes in, and then you just remember what it means, so it also ties in physically. That's what you want to know. What is that lambda? And if you know the lambda in each voxel, then you know the radiation distribution, which should be proportional to whatever, you know, chemical or biological process you were inducing to concentrate them something other than just uniformly.
So tall is kind of like our convergence measure.
Yes. So tolerance is, you know, and I've always abbreviated tolerance tall. You know, it's how far apart, right? When you're looking at two successive areas, one way you know it's converged is they get closer and closer and closer. Sometimes they can initially go the other direction, because you sometimes pick a wacky way out there one, and it might be a little bit slow, particularly if it's a nonlinear function, and then it'll pick up a little bit, and then it'll start going again, you know, depending on where it is within the nonlinear convergence. You know, but once it gets down below some point of that difference, you often call it done. Yeah, because you don't actually know the answer.
Right.
So you can't say when is it close enough to the final spot. So you have to go with, you know, when it's not changing enough that this would be too slow an update. But you literally do want to make sure that that's too slow an update. Otherwise, it will stop too early, and there still could be quite a bit of distance to go. There are other conditions we can add in. I just kind of put these as some basics. All right, this I just gave you because this is mostly just initial condition stuff. You know, setting lambda equals lambda 0. Lambda 0 is what they're passing in. But in each loop, we're going to be making a lambda. And so I initially say set my lambda equals lambda 0, so it's nice for next. We're going to compare that to a lambda next. Now, I can't actually, when I'm doing this, the last difference, I really don't have a last difference, right? Because I'm starting the whole thing. So I just guessed whatever your guess is. Now, that could be ridiculously small, right? Because if somebody's lambda 0 guesses 0,
right,
then that norm is going to be 0. So that's why you also have to be a little bit careful with the tolerance. So at the end, I'm going to do a couple checks to make sure, including if it gets bigger than the last step, no matter how small it is, I'm not going to jump. Because this first one, it's possible that your guess could be below the threshold to stop. Right? And it's possible that it stays below the threshold for a little while as it kind of tries to warm up to move into a spot where it can go, particularly if it's nonlinear and there's like some flat regions and then steep regions, and it goes kind of like a roller coaster ride. It can be really slow at the start and then all of a sudden it goes. Optimization can be like that when it's a highly nonlinear function. So anyway, you can have some of that oddness. As long as it's bigger than the last one, we'll also keep it going too. So there's a few things like that. And I don't actually calculate the difference here. I just say, hey, it started at 0 and goes to here, which might actually be nothing anyway. We find out how big that lambda is. That just gets us that's the number of boxes. Because there has to be, one lambda value per box. So that's a good metric for what our box is. We're going to assume that our picture is basically square for the most part. So we're going to take that square root of whatever that length is. And we floor it because I can't do fractional counts. So it is possible that the other one could be odd. So I just knock the m out of it and away you go with the rest. And then we've got, of course, our calculate our d, which is the number of observations. That's our detectors. Right? So that will be equal to the number of measurements we have to go. So now we've got all of our basic things done. I just set not done to be true. I'm not even going to test it now. I just go. And I set my iterations count because it is possible that you could set a max iterations. There are sometimes you set that too small. So anybody ever do any numeric stuff? Take a numerical linear algebra course or anything like that, scientific computing. So it's sometimes you just can't get precision below a certain point. A lot of it will depend on how you do your calculations. That there is, even though in theory double precision gives you 16 digits of accuracy, your calculations often will not get you anywhere close to that. Standard type stuff that's not completely naive. A standard reasonable algorithm will get you about half your digits of precision. A really good one will get you about 3/4 of the precision of it. To get all the digits takes a lot of work, a lot of very good math to solve these up. And you just have to be really careful how you calculate stuff. Like I mentioned, sorting in advance and summing up from small to large gives you a more accurate answer, for instance. So there's a lot of these kind of rules. If you ever have to get into implementing software for calculating things, and it's something other than trivial, then you should probably at some point take either a numerical math course or take the name in computation is scientific computing. So it depends on whether you're taking it from a mathematician or a computer science person. But the same course, just different names. But it's really important to get some of those details. I happen to love that stuff. That's actually where a lot of my work's from, but I don't really have time to go over a huge amount of it here. But I do want you to be aware of those type of calculations, that how you calculate it will make a big difference. And don't assume you can ever get better than half of your precision unless you know what you're doing. Okay. So now we want to calculate the denominator. I don't know if okay, I did. So denominator, the second line. I now want you right after that, while, right, not done. I want you to write something to calculate this, right? The probabilities times the lambda, and it's got to be summed up across all of the b's for a particular d, right? And I need those values for every single one of them, right? So that means I'm gonna have to do, how many, is this a single nested or a double nested? Double, why? You're right. Yeah, I have to do it for all of these, right? Because this part here is this, which is inside that sum, right? So you have to calculate it for every D. So which should go first, D or B? D should be outside, right? Just because of the way it's written, it'll cause you to need less memory, right? You'll be able to use scratch variables and then clear them out and reuse them and things of that sort. So we in essence need a double nested for loop. I would create a vector to hold it. How big should that vector be?
What are we holding? All the denominators?
Yeah, all the denominators, right? Because we're going to have to calculate them and hold them because we need to use them over here. There should be D of them because we have to sum up over D. So this should be a vector that's that size, the number of detectors.
And the P input argument, is that going to be a two-dimensional D by D?
Yes,
Okay.
there should be boxes and detectors. All right, and remember, that's actually what I called it coming in. On mine, right, it's the very first parameter coming in. So they should have it set up in this. I tried to write all my equations consistently, which is not actually in there in the literature. I would encourage you to get used to doing this step. I mean, it may look trivial, but by getting your nomenclature consistent and writing a little slide that has the actual math written in the correct nomenclature, you're not trying to figure it out later and mixing variables and getting weird stuff. So that is a very helpful process. So I'll put this back so you have the equation up here. Right now, all I care about is the denominator. You don't need to vote right now. I would just pull up that lab and try to follow along. So if you have your stuff from last time, or just pull up the script. Where's your show? You all good? Okay. Which one's this? So that's the one that makes the data. We're now generating a different function that will then recreate the image from it. Okay. So that's how we fake our data, or simulate it, however you want to think about it. Right. Since we don't have a subject and a scanner. So
Let's see that slide real quick. Just to see the function.
and you can copy the comments later.
Yeah, for sure.
And I'll go to the next slide in a few seconds, but it will have all the other stuff on it.
Sure. Thanks.
Okay, does everybody have? One, two. All right, so this is what I had for mine. I initialized the denominator to zeros. And why was that we do that?
Just memory allocation.
Memory allocation. It's all about the memory allocations. And it's where it goes. Is it a statically allocated or dynamically allocated variable. So it technically pushes it as part of your heap, which is on the stack, and there's only so much of that. So you don't want to waste that also. All right, and then we just walk through all the detectors, all the boxes, and that is just a straightforward calculation of that summation. Right, standard running sum equals running sum. We just have to do it over all the detectors D. Right. So that gets me my prediction of what I would expect each detector to have received. Because, you know, in essence, lambda is that mean, and P in essence is containing how much I should have of those, right? How likely it is to get picked up and detected, and the photons to make it out, things of that sort. Right. So after that, right, we've used up all of our space. Now we go up to the top of the next one, right? And I have to walk across all of the boxes, and I have to calculate numerator and the sensitivity. Which I think I recopied the slide one more time. But I did. Okay, so try to turn these equations now, right? So I just noticed, right, I've switched my order. I'm summing up over the boxes. Why am I doing boxes first now? So look at what's inside. What's explicitly needs a for loop?
Where are we talking? Just the whole expression?
We're now having to do, we're doing numerator and sensitivity, right? Those are the two we're adding. And inside the code, I gave kind of a hint on this one that I wanted you to count the boxes on the outside loop, right? On the previous one, we wanted the detectors on the outside loop. Why switch the order? So,
So do you do
I
the
see.
numerator and stuff at the same time?
yeah, see, I still have, right, this used up all the stuff, right? So now this is over D, right? When these all get, this is just D dependent. When I do over the sum, the D goes away. Right? I'm summing up over D. In essence, that D goes away. I'm left with box. So this is of size box. And I have to calculate them all. So again, it makes sense for the outer loop to be box. So I can do running sums. Right? You know, you could do it in the other order, but now you're going to have to hold all of the running sums instead of just one of them. Right? If you put the detectors out, since in the end I need boxes, if detectors is the outside loop, you have to, you know, have the running sums over both. It's not a very efficient way to do it. Whereas now we could just do running sum, we could just do one at a time. So it just needs one temporary variable in essence, well, one for each. So both of these are the detectors. But you have to calculate it for all the boxes. But boxes is what you're ending up now. So just like last time, detectors was the size of our variable. Now boxes is the size of the variable we're calculating. So other than that, this should again be a pretty quick writing. I think you're going to actually notice these are really disgustingly simple equations if you break them up right. If you don't break them up right, they're confusing as all get up. If you were to just go to somebody and say, hey, give me an expectation maximization procedure for pet data, you would not expect it to be this simple. But it really is this simple if you break the ideas up. Now, the world is actually nowhere near as complicated as everybody makes it out to be. Right? There are some real complications, but it's usually just because we don't get it yet. Let me know when you come or if you need help with something.
Let's see the.
What I'd ask is just get a couple white lines and try to code up this, right? Because that'll be better. I get you'll be able to copy and paste the code from the other one. More important is, can you take a look at an equation and turn it in? Assume you have the variables, and I use those names. So I call them P, and they're indexed by B and D.
Okay.
Right? And Y is the variable name, and it's indexed by D. And denominator is what I called that variable. It's indexed by D. I didn't put that one in, but because I didn't index it here, I want you to figure out denominator as sum over B, so the B goes away, only D is left. Right, so it has to be indexed over D. Right. If you get used to that thought process, you can look at almost any equation and figure out, how do I have to index it? What's the size of it? How do I write my loops? That's a good procedure, right? So just look at like the numerator, right? When you see a sum, you think for loop. For loop, and it's indexed over D, right? So you just write it from, little d is my variable, and capital D is what we calculated as its maximum, so it's 1 to capital D.
Yeah, I got a question. Would
Sure.
we also, after this, could we in this like 2 for loops also calculate lambda k plus 1? If we just multiply them all together and divide.
You could do this inside that. You have to do it in the B, not in the D. And you would have to, do it in this, the order of the B can't be the inner one. It has to be the outer, right? If you flip the order. Now, it's my personal, if I was writing it, I would not actually do that there. And the reason is, somebody might flip these to try to get memory access order. Right? Since I've indexed them in different orders, it is possible. One of them is row-wise stored, and so it'll be better in one for loop than the other. So to get speed, they might want to flip the order. And if I pull that one out to a second for loop, the second for loop doesn't cost me any more time than running it inside the same for loop. But it does allow you to switch the order of the loops by pulling it out to be able to maximize memory access. And caching of your variables, depending on whether they're row or column wise, is fairly crucial. And you don't want to get something out of it. So my general rule is split them up, and it makes it easier to optimize later on. When you first write stuff, a lot of people want to write really efficient code. It's the worst thing you can ever do. Write ugly, clean code. Right? Ugly as in not fast, right? Just write very simple, plain, clean code. Because once you do that, you can now look and examine, where's my speed getting killed on? Is it getting killed on cache? Is it getting killed on memory operations? Is it, it almost always comes down to arithmetic intensity, right? How many calculations are being able to do, or memory starvation. Are you able to pull the bandwidth of memory in to load it quick enough to feed it, right? And it'll either slow down on memory operations or on calculations. And it's pointless to speed the other one up, right? So you then ratchet. If memory is my slow thing, I work on cache efficiency and stuff like that. And at a certain point, that one stops dominating. My time starts getting used up in arithmetic. And I do arithmetic. And that kind of back and forth gives you a very simple, efficient way. Every optimization you do saves you time at that point. So that makes a nice methodology for being able to do it. And when you get partway through, so this is a little bit of how does your brain work, right? Anybody ever have trouble writing things efficiently? And part of the reason is most people start writing and editing at the same time. Your brain cannot do that. They're different functional areas, right? The same thing's true with code. You can't generate the ideas and optimize in the same step, but everybody tries to do it. And that's what actually kills the efficiency for you. So if you just worry about writing, get it down, get it to work, and then worry about optimizing your code, your brain can move into that area. Once you go into the optimize area, you're not going to remember what you did to generate it. That's not where your brain is, right? So that's why it's better to separate them. So that might be a long-winded explanation of why I want it. But I want you to think about that. It's much more important than one piece of code that you're never going to use again. Well, you might use it again, but it's not hugely likely, right? But the process, the ideas, you will absolutely use your whole life. So I care more about those. All right. We good? Okay, so here's what I did for mine, right? Inside that B, I pre-initialize, of course, num and sense. Right? Those are just kind of running values in here to sum up, because like I mentioned, I can just use those for them, right? Then I've got my 4D, and I just walk around, right? And I add up those, right? So at the end of these loops, we're going to have to use them, otherwise I'm going to lose my data, right? Because it'll get destroyed next time around. So I have to add some more stuff in here in a sec. But this adds up inside that 1 to B. There's going to be more stuff inside the 1 to B. Right? But inside here, this cleanly adds up the number. Right? What am I doing with the if? Right? If there was anything you didn't get, it was the if.
Kind of prevents.
Yeah, be careful you don't do division by 0.
Okay.
Right? That's really what that is, right? What would it mean for that denominator to be equal to 0? Remember, denominator was lambda times p. Lambda is what you think is there, right? And p is basically, if something is there, can you actually find it? Right? How sensitive are you to it, right? It's the likelihood that an event gets generated, and that if it gets generated, that your detector pair actually can detect it. If, in order for you to have a denominator to be equal to 0, that means either that detector pair cannot see it, in which case there's just no chance for it ever to be any different, right? Or you're saying that there was no concentration that was on there, right? And we're technically multiplying, right? So if it starts, the second it starts out at 0, you're kind of doomed. So we actually don't want to ever start at 0, even though I mentioned, hey, we start at 0. That's where most people kind of think, because we're doing addition. We're not going to actually ever want to start at 0. And this is where you can notice that. Because if I ever have lambda equals 0, right, the denominator will stay 0, which means there's no chance I could have picked something up, so it can't ever make an adjustment. Right? Now it's possible I just can't see that particular box. There could be other ones along the chain, but that box is in deep trouble. So I don't want to actually do a division by 0, but it actually has a physical significance. It means that thing is essentially non-updatable. So that's kind of an area to avoid.
Dr. I have a question. So I understand why the if case there, but I don't really understand why the else case is adding what it's adding. If the denominator is 0, are we just adding the same thing but without the division?
Yeah.
Is that,
So the numerator part, right? On that one, if you had a y, you have something. Now, there's a couple things we could do. We could just throw that completely out, right? If there was something in the box, but it's undetectable, multiplying it by p will make it go away.
Okay.
So it's not detectable. What we have there still won't add anything to it. The only thing this will do is if there's something there now in the actual measurements, and it's possible for that measurement to make an effect, then it will, in essence, allow there to be an update. And it will not get you the right answer. But if somebody wildly guessed a 0 wrongly, this one stands a chance of perturbing lambda to be able to undo what I just mentioned. What if somebody guessed badly?
Right.
And they guessed it too small and it just touched 0 temporarily? Then it would technically get killed and it would never come back. By doing this, I'm actually giving it a chance to restart. Okay? But it will only restart if your data says there should be something there.
Right.
Which meant not only was there something there, but it got detected. Right? So your lambda should not ignore that. So this is my way of kind of bootstrapping it back up. Yeah. And hopefully eventually it'll kick my lambda up and then I'll be in the upper one from then on, which will let me converge to the correct answer.
Right.
So this is a wrong error just for error correction. And that so I'm glad you asked the question. That is actually an important idea. Think about with your error correction ideas, how to make stuff work again, right? Because we were talking about before class started, how things can run sometimes for a week or so and then you lose something, right? Imagine it ran for a week or so and one of your variables touched 0 and never got back out again, but it should have got back out again. And you find out a week later and you're trying to make it to a conference submission deadline or something, and your data just got killed because of a coding error or an initial condition error, right? I mean, at that point you want to kill somebody, right? It's really annoying. So writing defensive code like this that will protect you just is all to the good. We good? Okay, so now again, notice I'm still inside B. Now I want to safely combine our calculation to get our next step, right? And again, this is a memory saving operation. In the long run, if I was doing my own personal code that I was going to release to people, it was going to be a library, I would split it out. I would just calculate, I'd make num and sense a larger variable, and then I'd break it out so I could get efficiency. In our case, we're going to do small stuff. So I'm going to try, in this case, just to simplify, less memory taken up, a little bit smaller code. But you could actually break this again into another for loop, like I had mentioned, and you could actually make it so you could optimize. So this one is a little bit harder to optimize. All right, but now we have to combine them. I don't think I put in another one for this because guess what you got to do? Divide, yeah. I mean, this is a pretty simple one for your lambdas, right? You've already got an index variable b, so it doesn't get much prettier than this. Good. Oh, I did. Oh, well. I didn't think I did. All right. So, again, it's a very simple one. But whenever you're saying division, your first thing should be make sure I don't have something equal to 0. And this is actually not even the best code for doing that. What should I really do? What should I be concerned about on division? Is it just division by 0?
Really small?
Really small numbers. All right. Normally what we want to do is make sure that sensitivity is not within some epsilon of 0. All right. So I would actually take a look if the absolute value of sensitivity was bigger than some epsilon. MATLAB has predefined EPS. It's a variable. So if you just type EPS and just hit enter, you should see 2.2 times 10 to the negative 16th. Anybody know what that is? It's machine precision. It's the smallest number you can add to 1 and get something other than 1. Right? If you pick anything smaller than that and you add it to 1, you get 1 again. It literally makes no change. So that's considered how accurate your machine is. Now, in reality, when you're doing divisions, that's not the only number that matters to you. But in general, if you're dividing by something about the size of machine precision, it probably could go pretty bad pretty quick. Because 1 over epsilon means you gain 16 decimal places of slide. That's gigantic, right? So you probably don't want it growing that fast anyway. So usually you'll pick some term that is kind of like this division by this number will cause too big of a growth. And it'll depend on what you're doing. With matrices, there's some other ballparks. Usually we use what's called a condition number for the matrix then. The ratio of the largest to smallest singular value. It can also be respecified in terms of eigenvalues. All right, good. We're almost done. All right. So now we have to figure out how to finish this. So I wrote in kind of text terms. These would actually be fairly decent comments to put in for it. But here are some of my ending conditions, right? We have to, if we reach max iterations, we're still done, right? If we haven't reached max iterations, and the system is still improving, right? We want to go, and we define the system as improving if lambda is bigger than some tolerance, right? That was our, the change, the update, right? That's why we need the difference, right? The last lambda, or lambda and lambda next type of thing, because I've got to be able to calculate that difference in some sense, right? And we also, if it's growing, then even if it's really small, we're still going to let it go. All right? Because remember how we said somebody could have started with a bad number and it could be really slow. The first round is going to run anyway, and if it's bigger than that first round, but the first round was too small, we're going to let it keep going as long as it's growing. Once it starts turning down again, then we'll say, okay, it's good enough at that point. And then there's a little bit of setup for the next round, right? Just remember there's iterations. So you have to set up the variables, such as also the not done. So you have all my variables, some of which won't change. So,
Yeah.
how's yours going?
It's all right.
Is it making sense
Yeah,
at each step?
that has mixed, for these areas.
So we're gonna,
next is next.
so remember that's, in this one, we're setting up the condition for the while loop. So you're gonna make a Boolean statement, and then just set it equal to not done. Right? And then that while loop will do your if. So just calculate those true statements and combine them appropriately into not done. And think about the area. Not done if it's 1 means keep going. Right? Not done equals 0 is your exit criteria. So you don't actually have to do the if here. But like for instance in MATLAB, you can make the statement. I could take if x is bigger than 5, right? That's an if statement to check that. I could also say, you know, my condition is equal to x is bigger than 5, right? And then I could say if cont, right?
Yeah.
In this particular case, I'm doing this style. And the reason is, if you're just doing x equals 5, who cares, right? But if it's, you know, x greater than 5 and, you know, absolute value of y, you know, is less than 10, you know, or, you know, some big, long, crazy chain of it, it would be easier to do some things where you would break logical groupings of these into different statements, like maybe this is checking, you know, an x and a y position, and it's checking to see if it's in position 1, you know. So then I could say position 1 equals, and I copy this whole thing in, you know, and I could have some information about position 2, and I could say position 2 equals, now that's logical thing. And then here I could just say if position 1 or position 2. That's a lot more readable. Right? And so I'm just suggesting you get used to, rather than stringing out a bunch of hard to read conditions, group them together into a variable and then kind of assemble them. That makes it human-wise more readable than having like 20 or 30 things cascaded.
Question.
Sure.
So you mentioned that if the difference from our previous lambda to our next lambda is less than some threshold, we might end. But if someone made a bad guess and it's still growing, we wouldn't end. I'm trying to think of a good condition to test for that.
So what you want to do, if it's still growing,
Right.
then your difference now should be bigger than your difference last time. Right?
Okay. All right. I wasn't storing the last tip.
Yeah. But you notice I have it there. If last.
So, are we for the
And notice I built my lambda here, I'm doing lambda next.
Right.
Right? And lambda, that way I can compare the difference between
Right.
those, right? And you'll have to appropriately copy over afterwards. But you also have the difference from last time, which will be.
I see. So I have my diff last and I subtracted them. So I want like more than half of the of them to be correct?
Yeah, so that's up to you. Like the simplest thing would be if it's bigger than, you know, if my current diff is bigger than diff last, keep going, right? For different scenarios, so I'm trying to give you some areas where you'll sometimes see this in convergence areas that'll be on these. And you might look at it and say, oh, it's really kind of going slowly, you know, but it's got a really flat region. And so some of these type of conditions let you keep it going, but not unnecessarily. Like you've reached the bottom and you're just bouncing around the bottom. You want it to figure out to exit, right? But if it's slowly progressing and moving, you don't. So, you know, in this case, just holding that diff last lets you see that. There are tons of other ones that are out there. It's more getting used to, oh, these type of things can happen. And it happens particularly when you see kind of like some oddball ones, like particularly if you get, you know, an optimization problem that kind of goes out and it flattens, you know, but you could have, you know, if you're going out into this plane, it could be really high. So it's possible that you have something that comes down here right, from a high zone, it falls over to this outside, and eventually it starts falling back in. And what you don't want is in this zone here, when you flatten out, right, because you're coming from out here and it's really steep, when it rolls off to this kind of saddle point, before it slowly goes, oh yeah, there's another direction. Right, and that's kind of shape-wise one of the shapes that causes problems in those optimization areas, heading towards those flat regions for the optimization. Good. Okay, so this is my stuff again, right? So, you know, delta for lambda, it's just the difference between the two of them. I just took the norm of that, that's my difference. I increased my iterations, and then my not done is just going to be equal to difference is bigger than the tolerance, or difference is bigger than difference last, right? And iterations is less than max iterations. Notice I made this or I grouped together. Good. Yippee. All right. So, after you've done all that lovely stuff, right, we want a little bit of debugging. So what I want is two different conditions, right? I want a basic one that'll just print some key numbers, right? Some things like, what is my difference and what's my particular iteration range, things like that. So if you set your debug level, think of debug level as just an integer. If your debug level hits this basic level, say 1, I want it to print out, give me some numbers you think is going to be fairly important, right? How big is difference? How big is iteration? That's dead minimums. You might pick a couple other ones that are important, right? There's potentially a more advanced one too, where I can actually print lambda. Because remember, lambda can be reformed into a matrix to see an image. And sometimes by just looking at that image partway through, it'll show stuff up. If you want to be really fancy when you do the print for that one, you either are going to need to make it a separate slide or give me a pause, right? So that I don't care which one you do. If you're saying your max iterations to 10, maybe you just want all 10 of them, right? For the print on this. But this should be like a debug level of 2, right? I get to show me the picture. But I want it such that if I ask for the picture, I want the numbers too. Alright, we have something? Alright, so I checked mine, right, if debug's bigger than 0, and then I use display, right? Display, display is both very nice and really annoying, right? It's really nice in that it's simple, it works even if it's deep within the area, it'll format a single variable. But if you want more than one thing, it doesn't format it at all. It can only take one thing going in. And so in order to do that, you now have to pass it a string that is in, anybody know what that format is? fprintf, where that came from? That's C's printing style. So if you're used to C++ with, you know, C in and C out, this is actually prior to that. This is early 70s, late 60s programming. You had these, you know, technically fprintf means a file print formatted is actually where that came from. You'll see they've got different types of printf. F goes to a file, but that also includes with inodes and that, you can redirect it to the screen and things. That still counts because it's a stream buffer for that. So it still counts there. There's a couple different ways you can go. But anyway, it's got a format. %D, everybody know what D means?
Integer.
Decimal. Yeah. It's a decimal integer. So it's an int number, but it's in decimal. You have actually several different decimal ones you can pick. The % means I'm going to pass you a variable. %F,
Floating point.
floating point. Yeah. That's in. And so I pass a couple floating points, and I've got otherwise the normal text goes. So it's going to have %D, a blank space, you know, norm equals %F, comma, right? So it'll actually reproduce that string, and then I have the list of variables that get substituted. So this is the old string printing thing. You could actually do this in two things. You could set a variable and then pass it in. You know, this is debug code, so I don't think of this as particularly maintainable. So, like, I'm all about making normal code highly readable, right? There are also areas where you don't want to put that effort in. If it's something you care about and people might update, then definitely you want to do that. If nobody ought to be changing debug code unless they really know what the hell they're doing, right? You shouldn't touch code unless you know what you're doing, but you really shouldn't touch debugging code unless you know what you're doing. And then, you know, it's one-offs. So I'm not going to sweat it. Somebody's going to comment mine out and make their own, you know, or add another debug level. And then I did mine with making a bunch of figures. And I did that because I assumed I had a small number of max iterers. Plus, I already showed you a pause one of the previous ones, so I figured I should do one of different ones. You know, and I put the second one inside. That actually is probably a bad format. I really should have had that end, and they should be two completely independent ones. But it's technically, if you're going to have debug bigger than 1, it's going to be bigger than 0. So it's not like it'll cut anything out, but probably not the best. So, all right, we feel good? We're at the bottom of the page, so that's as far as you need. I mean, it's literally, yeah.
Is there an extra end in there?
I don't think so.
The top of the right column, the 4B equals 1B, that end is right above Delta L.
Okay.
It's not formatted, but there's the correct number. And then the while loop ends
Should be.
way down,
yeah.
the second to last one. The function.
And then the, yeah.
They're a little.
It would be a little bit better to put a comment and say what each one is. So that's the nicer way to do this, and I'll admit I did do this one nicer. You know, and so the nice format is to actually go in and just put comment character and say function, comment character and say while, right? And for each one, right? This one comment if comment, you know, and you can actually, you know, if debug bigger than 0, if debug bigger than 1, and you can walk back that way. And if you do it, then you can look at any one of the ends and find them. If the code gets multiple pages long, I do that. On that, I just kind of wrote this and cranked it out. Yeah.
Also, another thing that happens is if you're in your own script and you have an end you don't know what it is, if the start of the block is off the screen, you can put your mouse over the end and it'll show you the line that was on. So
Yeah.
I find that
No, that is. There's a lot of cool things if you go in. You can open and close groupings too, which is actually quite helpful. So you can hide stuff to see the basic flow. That's a really nice feature too. So, absolutely. You know, do whatever you can. The other thing that I would say is, I'm not going to say I make the best variable names in the world, but I try to make my variables such that A, you know what they are, and B, when I write a line, it reads as English, right? Like my loop variable, I could have just called it condition, but I called it not done. So you could read, while not done, right? Essentially, it removes the need for you to put comments. And in general, I don't like comments unless I have no choice. And part of the reason is, even if I make my comments correct, somebody else is going to come through and edit something and they won't update the comment, which means the comment's going to get out of place and it's useless. So you got to do something to force it to be fused together. And this is about the best way I know. This, I think I've mentioned, this comes from an idea called extreme programming. So, all right, we good? Okay, so the last thing is we just need to test the code. So I've got the blank space in the middle that separates. The first half is setup, the second half is run it and show it. So the upper half, right, you'll see I just set my things, you know. How big do I want N to be, right? How many detectors? I have to make a phantom of that size, right? So N is just going to be, I'm making a square image. That's just the size of my image. I'm making a 60 by 60 image with 90 detectors, right? And so you get your geometry. I see, initially I set it to zeros, but then I put a concentration, right? All in one central area. So I just made a block, you know, it's a square that literally has everything, right? Kind of mimicking a tumor. You could do whatever type of spread out things you wanted, but this is going to be pretty significant because when you watch this, we're going to do so few decays and everything that when you take a look at what's your standard, you know, least squares solution will generate such a bad solution that you won't even get a square. It'll look like a firework exploding. You know, whereas when you do EM, you're going to get a square with potentially a couple of fringes on the side. It's a night and day difference. But that's why I picked these. Honestly, I picked them to embarrass least squares. Right? Which maybe that's not a good goal in real life, but I do it so that it underscores to you where one is useful versus the other. This is way slower, so why do I do it? Give you an extreme case where it makes a difference. T, that's the time periods. Again, remember, more time periods, more decays. You know.
did you mean to put a comment after the semicolon after the point?
Yes, it should be commented out. Actually, no, this equals 1 should be there. Debug equals 1. I must have pasted this up and then accidentally highlighted and dragged it. So thank you for finding that. Yeah, that's sometimes when I'm cutting and pasting stuff and I try to redo stuff, it'll grab things and I don't notice where it grabbed it. So. Yeah. This is what we wrote a few days ago. That's fake our data. Right? Then we're reshaping this into a single vector. right, to get our lambda 0. So I just make, initially I'm guessing 1s, and then I'm taking the norm of b, so I'm making it the same size as what the data should be, and just spreading it out in equal amounts. So I'm just getting a uniform constant level. That's all this is doing. So my guess is a constant. I set my tolerance to 0.01. It's sufficient to let it run for a while, but not go too crazy. Then I just run my code, right? After that, I get, in essence, my image back, my lambda. I reshape it, and that's my concentration map. So make a figure, subplot it. I put that, call it EM. Right? Make a second one, that's the true value, so I just show IC, that's the actual thing. And then in the far right one, I just reshape A/B, that's least squares. And this is done, you're not familiar with that?
Oh,
notation?
I was.
Yeah. Right, A/B.
Directly.
Yeah, I just stick it in there, calculate it one unit. I mean, you could have done it as a separate variable, but I don't care about it, so, and it's such short notation, it really wasn't worth making a variable for it. And using the / operator, the MATLAB does as good as you're gonna do for least squares, it does it, and reshapes it, and then I title that least squares. So it just gives me 3 plots appropriately labeled. If you've got everything, you should be able to run it, and like I said, you'll see now. You'll get something that will look like, a figure window will pop open. You'll get 3 pictures. The middle one's the true one, so you get this little square of concentration. You'll get a square of concentration here with potentially some fringes around the side of it. And for the least squares, it'll literally look like a sunburst. It's basically useless. If you increase the number of detectors, you increase the time period, stuff like that, you'll find least squares will get better and better. But that's not fun. Basically meaning if you've got tons of data and it's good data, don't do EM. It's slow. If you're on the ragged edge, do EM. It'll pull it out. Has everybody tried running them? I don't know if I think I put some pictures up on it. Nope, I did. I thought I might have stuck the picture from one. Bad me. I should have stuck the screen capture there. So you just get my only fake pictures. Except when you run your account. Did anybody get errors?
I got a warning.
Oh yeah, you'll get a warning.
Okay.
Then the warning it's going to give you is that this is a really badly conditioned matrix. Least squares is screaming bloody murder because I've got 90 pairs of or 90 detectors to be able to figure out 60 squares. Yeah. It's just, I do have some pairs of detectors, but there's not. Yeah. Here's red. See how you can still see the box there?
Right.
You can see the white box. It's in the right spot.
Right.
It's a little bit noisy.
Does that look reasonable, or do you think I did something wrong?
You could have an error.
Okay.
Mine looks cleaner than that. But the least squares,
Correct.
although it is still, notice you're still missing in that area. So I'm thinking you might have, something wrong with the lower part of your screen.
Okay.
So it might be worth walking through some of your data and seeing that it actually, when you go through, you might not be getting the lower part of your screen. So I would check it might be in your detector pairs when you're generating them,
Yeah, because it's one spot. I'm thinking.
because it is a strangely dead zone for possible. Okay. What'd you get?
How much? It goes into government this one. So when it's nominated, it goes to 0. It says Michael pass.
Because you do B is 1 to D. Which should be capital B, not capital D. There's different numbers of boxes in there. So check and see if that. That is the danger with B's and D's. They look quick, it's hard somewhat. Yeah, I'm dyslexic and it's dangerous, but.
Yeah, I just got it.
Yeah, you'll get a warning. You'll- Yeah. Yes, it should be every bit as bright. So there might be a normalization factor on yours, but you are getting the right shape in the right area. And that is what least squares looks like. So the fact that your least squares looks correct probably means that your data is correct. Right? Because if your data was wrong, then least squares would be wrong.
Yeah, I just.
Right? It wouldn't give you that nice uniform wall. Right? So probably somewhere when you're calculating it, you might be like missing a denominator, or it might not go through the right number of iterations, so it's not normalizing, something of that sort.
Under the comment, 2 time periods.
But your data, so I wouldn't expect anything in the make test.
Yeah, that you can.
It's all gonna be in
one
the
line down.
Mhm.
Because if it was a make test, you'd see it in least squares. So that's the other reason why it's nice to use, even though least squares is bad for this, it at least lets you quickly slice out a lot of data. Yeah, so that is helpful, just holding it, right, walk through them, and you can see.
Yeah, that did look a little suspicious.
Did you see anything go through here? Because I saw a bunch of them coming down the edge, but
They do, but it looks weird. It looks like it should, the way the formulas are set up, that should
so,
be-
but see how that's walking through? It's missing that lower half. So I don't think you're walking through those correctly.
Okay.
Because it is literally walking around this shape down here.
Right, I see that. Yeah.
Right. And it should be walking through all the ones around.
Right.
So I'm guessing that they're, can you show where the detectors are first?
Yes.
So this is the first one to check, just to make sure the detectors are in the right spot.
So that one was. So this is the bottom of the detector.
That's beautiful. So they're in the right spot. So now I'm thinking it has to do with your for loop walking through them, that the numbering on them, it's missing some of the number range. So I would check those to make sure it's grabbing all the pairs once. Yeah.
So I got a couple errors.
Unrecognizable variable n, which I can use from here.
Okay, so there should be. And this is on your make. So that means you missed the end variability. Let me pull up the one for make that. So you're missing this line.
Here.
That's easy, this one. We are past our time. So let me at least stop the cameras and everything. Yep, maybe it stopped on its own.